Welcome to today's paper reading. Today's paper is titled, Qwen2.5 Technical Report. This technical report introduces the Qwen2.5 Coder series, developed by Jian and colleagues from the Qwen team at Alibaba Group. The Qwen2.5 Coder series represents a significant advancement from its predecessor, Qwen1.5. This series comprises two models, Qwen2.5-Coder-1.5B and Qwen2.5-Coder-7B. These models are specifically designed for code-related tasks and are built upon the Qwen2.5 architecture. They have been pre-trained on a massive corpus of over 5.5 trillion tokens, with meticulous data cleaning, scalable synthetic data generation, and a balanced data mixture strategy. This approach has enabled the models to demonstrate impressive code generation capabilities while maintaining general versatility. The models have been rigorously evaluated on a wide array of code-related tasks, achieving state-of-the-art performance across more than 10 benchmarks, including code generation, completion, reasoning, and repair. Notably, they consistently outperform larger models of the same size. The release of the Qwen2.5 Coder series is expected to not only advance research in code intelligence but also, through its permissive licensing, facilitate broader adoption by developers in practical applications. The rapid development of large language models, LLMs, has led to significant advancements in code-specific language models. These models, such as the Star Coder series and CodeLlama series, have shown superior performance in coding evaluations. However, compared to proprietary models like Claude 3.5 Sonnet and GPT-4o, code LLMs still lag behind. Building on our previous work with Qwen1.5, we introduced the Qwen2.5 Coder series, designed to achieve top-tier performance in coding tasks. These models, with 1.5B and 7B parameters, are derived from the Qwen2.5 LLMs and are open source to support research. The models are pre-trained on a large-scale dataset comprising over 5.5 trillion tokens, sourced from public code repositories like GitHub and web-crawled data. The architecture of Qwen2.5 Coder is presented for two model sizes, 1.5 billion parameters and 7 billion parameters. Both models share the same number of layers, 28, and a head size of 128. However, they differ in hidden size, with the 1.5B model having 1,536 and the 7B model having 3,584. The head configurations also vary. The 1.5B model uses 12 query heads and 2 key-value heads, while the 7B model uses 28 query heads and 4 key-value heads. The intermediate size scales with model size, being 8,960 for the 1.5B model and 18,944 for the 7B model. Additionally, the 1.5B model employs embedding tying, which the 7B model does not. Both models share a vocabulary size of 151,646 tokens and have been trained on 5.5 trillion tokens. Special tokens have been introduced to help the model better understand code, such as tokens for the fill-in-the-middle technique and for managing repository-level information. Table 1 provides a detailed comparison of the architecture between the Qwen2.5 Coder-1.5B and 7B models. Both models share the same number of layers, 28, and head size, 128, but differ significantly in hidden size, with the 1.5B model having 1,536 and the 7B model having 3,584. The 1.5B model uses embedding tying, while the 7B model does not. Both models have a vocabulary size of 151,646 tokens and have been trained on 5.5 trillion tokens. Table 2 provides an overview of the special tokens introduced in Qwen2.5 Coder to enhance its understanding and processing of code. These tokens include end-of-text, for marking the end of a text or sequence, FIM_prefix, FIM_middle, and FIM_suffix, for implementing the fill-in-the-middle technique, and FIM_pad, for padding during FIM operations. Additionally, tokens like repo_name and file_sep are used for identifying repository names and managing file separators, respectively. These tokens are crucial for enabling the model to learn from various code structures and handle longer, more complex contexts effectively. The pre-training process for Qwen2.5-Coder is built on a foundation of large-scale, high-quality, and diverse data. The dataset, named Qwen2.5-Coder data, is composed of 5 key types: source code data, text code grounding data, synthetic data, math data, and text data. Each type underwent specific cleaning methods to ensure data quality. For instance, source code data was collected from GitHub repositories and filtered using rule-based methods. Text code grounding data was curated from Common Crawl using a course-defined hierarchical filtering approach. Synthetic data was generated using code Qwen1.5 and validated for executability. Math and text data were integrated to enhance the model's capabilities without compromising performance on code tasks. The data mixture was carefully balanced to include 70% code, 20% text, and 10% math, totaling 5.2 trillion tokens. The training policy involves a 3-stage approach: file-level pre-training, repo-level pre-training, and instruction tuning, each designed to progressively enhance the model's capabilities. Figure 1 illustrates the number of data tokens across various stages of the course-defined hierarchical filtering process and the validation effectiveness of training Qwen2.5-Coder using the corresponding data. The figure shows that through a 4-stage filtering process, the average scores on human eval and MBPP benchmarks increased from 41.6% to 46.8%, demonstrating the impact of high-quality text code grounding data on code generation tasks. Table 3 presents the performance results of Qwen2.5-Coder training under various data mixture policies. The study compared 3 different code, text ratios: 100 to 0 to 0, 85 to 10 to 5, and 70 hours 20 minutes and 10 seconds. Notably, the 7 to 2 to 1 ratio, which corresponds to 70% code, 20% text, and 10% math, demonstrated superior performance, even surpassing mixtures with higher proportions of code. This suggests that math and text data positively influence code performance when their concentration reaches a specific threshold. The final training dataset for Qwen2.5-Coder comprises 5.2 trillion tokens, reflecting the optimal mixture identified through empirical experiments. Figure 2 illustrates the 3-stage training pipeline for Qwen2.5-Coder. The stages include file-level pre-training, repo-level pre-training, and instruction tuning. File-level pre-training involves learning from individual code files with a maximum sequence length of 8,192 tokens, covering 5.2 T of data. Repo-level pre-training extends this learning to entire repositories. Instruction tuning refines the model to follow specific instructions, enhancing its performance in practical applications. Figure 3 illustrates the file-level FIM format used in the training of Qwen2.5-Coder. The format includes placeholders for code segments: FIM_prefix, code_pre, FIM_suffix, code_suf, FIM_middle, code_mid, in DOF text. This stage of training involves sequences of up to 8,192 tokens and focuses on objectives such as next token prediction and fill in the middle, FIM. Figure 4 illustrates the format used for repo-level FIM, file-level infilling model. This format includes repository name encapsulated in repo_name, tags, followed by file paths and their respective contents separated by file_sep, tags. This structure is designed to enhance the model's long context capabilities by extending file-level FIM to the repository level, as described in the methods of Laskov et al., 2024. In this section, we discuss the post-training techniques for multilingual code instruction data. First, we fine-tune a code-BERT model to identify programming languages, categorizing documents into nearly 100 languages. We selectively discard data from long-tail languages to focus on mainstream languages. Samples with no code snippets are classified under a no programming language tag. Next, we synthesize instruction data from GitHub code snippets using a large language model, LLM. This process involves generating instructions, filtering out low-quality ones, and constructing a diverse instruction dataset. Finally, we introduce a multilingual multi-agent collaborative framework. This framework includes language-specific agents that engage in structured dialogues to enhance language capabilities and generate new instructions. It also features a cross-lingual knowledge distillation technique to share insights across languages. To ensure the integrity of the evaluation results, the authors implemented a decontamination process to prevent inflated outcomes due to test set leakage. This process involved both pre-training and post-training datasets. Key datasets such as human eval, MBPP, GSM-8K, and math were removed to avoid any overlap. The filtering was conducted using a 10-gram overlap method, which involved removing any training data that had a 10-gram string-level overlap with the test data. This rigorous approach ensures that the evaluation of the base models is fair and accurate. The evaluation of base models was conducted across 6 key aspects: code generation, code completion, code reasoning, mathematical reasoning, general natural language understanding, and long context modeling. For code generation, benchmarks such as human eval and MBPP were used. Qwen2.5-Coder-7B base demonstrated state-of-the-art performance, outperforming DS-Coder-33B base. Additionally, the model was evaluated on the multi-PLE benchmark for multi-programming language proficiency, achieving high scores across various languages. Table 4 lists all the artifacts released and used in the evaluation section. It includes models ranging from 1.3 billion to 33 billion parameters. The models are evaluated on benchmarks such as human eval, MBPP, and Big Code Bench. Performance metrics include scores on HE, MBPP, and Big Code Bench, with specific scores provided for different model sizes. Table 5 presents the performance metrics of various models on 3 key benchmarks: human eval, MBPP, and the complete task of Big Code Bench. Notably, Qwen2.5-Coder-7B base achieves superior results compared to DS-Coder-33B base across all evaluated metrics. Big Code Bench Complete, designed for out-of-distribution evaluation, is divided into full and hard subsets, further testing the model's generalization capabilities. Additionally, the multi-PLE benchmark assesses the model's proficiency in 8 mainstream programming languages, ensuring a comprehensive evaluation of their versatility. Table 6 presents the performance of various models on the multi-PLE benchmark, focusing on their proficiency in multiple programming languages including Python, C++, Java, PHP, TypeScript, C#, Bash, and JavaScript. Notably, Qwen2.5-Coder demonstrates state-of-the-art results, scoring over 60% in 5 of the 8 languages tested. This highlights the model's balanced capabilities across different languages, underscoring its versatility in meeting the complex demands of software development. Table 7 presents the performance of various models on the human eval and filling tasks. Qwen2.5-Coder-1.5B shows significant improvement over models with similar parameter sizes, achieving a 3.7% average performance boost. Qwen2.5-Coder-7B base outperforms all models with over 6 billion parameters, including the 33 billion parameter DS-Coder-33B base. This table highlights the efficiency and effectiveness of Qwen2.5-Coder models and code completion tasks. Table 8 presents the performance of various models on the CRUX eval benchmark under input COT and output COT settings. Qwen2.5-Coder demonstrates strong results with scores of 56.5 on CRUX eval I and 56.0 on CRUX eval O. Notably, StarCoder 2-15B achieves a high score of 62.7 on the output COT task, indicating its effectiveness in predicting inputs based on known outputs. Table 9 presents the performance of various models on 4 key math benchmarks: Math, GSM-8K, MLU-STEM, and Theorem QA. Notably, the Qwen2.5-Coder-7B base model achieved a score of 46.6% on the math benchmark, while the DS-Coder-33B base model scored 35.4% on GSM-8K. These results highlight the varying capabilities of different models across these mathematical tests. Table 10 presents the MMLU results of different models, which is a general benchmark for common knowledge. The table evaluates various models across multiple dimensions, providing performance metrics that highlight their capabilities in handling general knowledge tasks. Table 11 presents the general performance of various models on 4 popular general benchmarks: Arc Challenge, Truthful QA, Wino Grande, and HelloSwag. The table highlights that Qwen2.5-Coder demonstrates superior performance in general natural language capabilities compared to other models. This outcome further validates the effectiveness of Qwen2.5-Coder's data mixing strategy in enhancing general knowledge and natural language understanding. The evaluation of instruct models focused on 6 core areas: code generation, code reasoning, code editing, text-to-SQL, mathematical reasoning, and general natural language understanding. The Qwen2.5-Coder-7B instruct model demonstrated superior performance in code generation tasks, achieving an 84.1% accuracy on Human Eval Plus. It also outperformed other models on BigCodeBench Instruct and LiveCodeBench, highlighting its capabilities in handling complex coding challenges. Despite its smaller size, Qwen2.5-Coder-7B Instruct surpassed larger models like Qwen2.5-Coder-1.5B and Qwen2.5-Coder-7B Instruct, showcasing its efficiency and effectiveness. Figure 5 demonstrates the long context ability of Qwen2.5-Coder, evaluated through the needle in code task. This task involves inserting a simple custom function at various positions within a code repository and testing whether the model can replicate this function at the end of the codebase. The figure shows that Qwen2.5-Coder is capable of successfully completing this task within a 128K length range, highlighting its advanced long context modeling capabilities. Table 12 lists all the artifacts released and utilized in the code generation section of the study. These artifacts include various models such as Qwen2.5-Coder-1.5B Instruct, Qwen2.5-Coder-7B Instruct, and Qwen2.5-Coder-7B, among others. These models are key components in the evaluation of code generation capabilities, as highlighted in the subsequent sections of the paper. Table 13 presents the performance metrics of various instruct models and code generation tasks across benchmarks such as Human Eval, MBPP, BigCodeBench, and LiveCodeBench. Notably, the Qwen2.5-Coder-7B Instruct model demonstrates superior accuracy, surpassing models with similar parameter sizes and even larger models like Qwen2.5-Coder-1.5B and Qwen2.5-Coder-7B Instruct. It achieved an impressive 84.1% accuracy on Human Eval Plus, highlighting its robust capabilities in code generation. Table 14 presents the performance of various models on the multi-PLE instruct format, which evaluates code generation across multiple programming languages. The Qwen2.5-Coder-7B Instruct model demonstrates superior performance, consistently outperforming models with the same number of parameters, such as DS-Coder v2 Lite Instruct. Notably, it achieves an average accuracy of 76.5% across 8 programming languages, surpassing even larger models like Qwen2.5-Coder-1.5B and DS-Coder-7B Instruct, which have over 20 billion parameters. This highlights the Qwen2.5-Coder-7B Instruct's robust capabilities in handling complex code generation tasks in diverse programming languages. Figure 6 illustrates the McEval performance of the Qwen2.5-Coder-7B Instruct model in comparison to other popular open-source large code models of similar size. The model excels in code generation tasks across a broad spectrum of 40 programming languages, as evaluated on the McEval benchmark, which includes 16,000 test cases. Notably, Qwen2.5-Coder-7B Instruct not only surpasses much larger models like DS-Coder-33B Instruct and Qwen2.5-Coder-1.5B but also demonstrates a significant advantage over models with comparable parameter sizes. Figure 7 demonstrates the correlation between model sizes and their code reasoning capabilities. Notably, the Qwen2.5-Coder-7B Instruct model, despite its smaller size, achieves superior code reasoning performance, surpassing larger models like Qwen2.5-Coder-1.5B and DS-Coder-33B Instruct. The x-axis of the figure represents the parameter sizes of various models, while the y-axis indicates their respective CRUX eval (COT) scores. This trend suggests that models around the 30 billion parameter scale could potentially match the code reasoning performance of GPT-4o. Table 15 presents the CRUX eval performance of various instruct models, focusing on input COT and output COT settings. The Qwen2.5-Coder-7B instruct model achieved 65.8% and 65.9% accuracies for input COT and output COT, respectively, showing significant improvements over the DS-Coder v2 Lite instruct model. This model also outperformed larger models like Qwen2.5-Coder-1.5B and DS-Coder-7B instruct, highlighting its superior code reasoning capabilities despite its smaller size. Table 16 presents the code editing capabilities of various instruct models as evaluated by the ADER benchmark. Notably, Qwen2.5-Coder-7B instruct, with only 7 billion parameters, achieves a 50.4% pass at 1 accuracy, significantly outperforming larger models such as Qwen2.5-Coder-1.5B and DS-Coder-7B instruct. This table highlights the model's efficiency and effectiveness in code editing tasks, demonstrating its remarkable performance despite its modest size. The consistent application of the edit format across all experiments ensures reliable and reproducible results. Table 17 presents the comparative performance of Qwen2.5-Coder-7B instruct and DS-Coder v2 Lite instruct across various math and general tasks. Key observations include Qwen2.5-Coder-7B instruct's superior performance in tasks like math, GSM 8K, Gaokao 2023N, Olympiad Bench, College Math, and AIME 24, as well as its improved scores in AMC 23, MLU, MLU Pro, IF Eval, CEval, and GPQA. This indicates Qwen2.5-Coder-7B instruct's effectiveness in handling a broader range of mathematical and general knowledge tasks compared to its counterpart. Figure 8 illustrates the prompt template used by Qwen2.5-Coder for text-to-SQL tasks. The template includes a create table statement defining fields such as last name, first name, grade, and classroom. It also provides example rows with data entries like CAR, Christensen, and Vanderwood. The template concludes with a sample question, how many students? Which is answered by the SQL query select count, from list. Figure 9 presents the evaluation results of various instruct code models on the text-to-SQL task. The Qwen2.5-Coder-7B instruct model demonstrates superior performance compared to the DS-Coder v2 Lite instruct model, excelling in 11 out of 12 tasks. This figure highlights the model's capabilities in both mathematical computation and general natural language processing tasks, showcasing its versatility and effectiveness in complex coding tasks. In this work, the authors introduce Qwen2.5-Coder, an advanced model built upon Qwen2.5, a leading open-source large language model. Qwen2.5-Coder has undergone extensive pre-training and post-training processes using Qwen2.5-1.5B and Qwen2.5-7B models on large-scale datasets. To maintain high data quality, the authors curated a dataset by collecting public code data and extracting high-quality code-related content from web texts, while filtering out low-quality data using advanced classifiers. Additionally, they constructed a carefully designed instruction tuning dataset to transform the base code LLM into a powerful coding assistant. Looking ahead, the authors plan to explore the impact of scaling up code LLMs in terms of both data size and model size, and to continue enhancing the reasoning capabilities of these models, aiming to push the boundaries of what code LLMs can achieve. Thank you for watching.